No chemistry class is complete without demonstrating the properties of sodium metal. Very unique metal, very unique properties in many ways. Let's first of all look at what sodium metal looks like. And before we do that even though, let's also look at how sodium metal is packed. Sodium metal is packed in what we call a safe store can, a Flynn Scientific safe store can. We have that in a plastic bag, twisty tied, and we have vermiculite in there as well. Now, the vermiculite, I've poured out most of it so that I wouldn't get vermiculite all over the surface, but normally the vermiculite would be about halfway through there. Why do we package sodium this way? Because sodium is a very reactive metal, and in particular, sodium reacts with water and with air, sometimes quite dramatically. And so if we open this up, and let me put on my gloves here so that I can work with the sodium metal. What we've done is we've actually cut up the sodium metal into very small demonstration size pieces. And that, again, increases the safety of working with metal. All of this has to do with the reactivity of sodium and keeping it as safe as possible. The bottle is about 1/2 full with mineral oil. And again, that's to protect the sodium from reaction with oxygen in the air. And these are very small pieces. I'm going to take some of them out and put them in this Petri dish. You can see the oil around them. And I have about 7 pieces in here. And again, we've cut these into just about 1/2 centimeter cubes or squares, just so that we can increase the safety of it. And so the first thing that I want to do is actually demonstrate that sodium is a very soft metal. You know, we think of metals as hard, but you can cut sodium with a knife. That's how we cut it to get the demonstration size pieces. So I'm going to take one of those pieces there and just going to demonstrate that you can just slice right through that. And I've cut the one piece into 2 pieces there. Okay. It's a very soft metal, but it is a very reactive metal. Now, many people do the demonstration on a fairly large scale, and there have been some pretty good accidents depending on the scale. That's a nice way to do it, but there's a safer way to do it that in many ways is a more effective demonstration of the properties of sodium, because we're almost going to look at the reaction in slow motion. The way that we're going to do that is I have a large hydrometer cylinder. Hydrometer cylinders are wonderful for doing a lot of different demonstrations. They really give you good presentation. They make it visible to the entire class and so on. And the first thing I'm going to do is fill that about 1/2 full, well, actually probably about 1/3 full, with water, simply distilled water. And I'm going to add some phenolphthalein to that water. Phenolphthalein, of course, is an acid-base indicator, and if a little is good, in this case, more is fine. So I've added probably about 1 milliliter or so of the phenolphthalein. I'm going to stir that with a stirring rod just a little bit, just to be sure that I'll get good mixing later on. One of the drawbacks of a hydrometer cylinder is it is a little hard to stir and get thorough mixing, but that will be good enough for our purposes. The next thing that I'm going to do is add some mineral oil. Remember, we said that the sodium metal was packed in mineral oil. And I'm going to add the mineral oil to the top of the water there. And actually what I'm going to do is hold it and kind of pour down the side. Now, mineral oil and water, of course, do not mix. So we expect to get 2 layers. And so I'm just pouring it down the side just so that I don't get too much mixing within the liquid. They wouldn't dissolve in one another, of course. But I just want to see that, and that should be fine. So I have some mineral oil, and you can see the 2 layers. The water is on the bottom, the mineral oil is on the top. What's going to happen if I add a piece of sodium metal to it? We know that sodium metal reacts with water, but I've got mineral oil there that's floating on the top. Well, the first thing has to do with the density of sodium. It turns out the density of sodium is about 0.97, so it's more dense than mineral oil, but less dense than water. So as I add the sodium there, it immediately goes to the interface and immediately reacts with the water. But one of the products is hydrogen gas. And so when it goes to the interface, because it's more dense than the mineral oil, less dense than the water. So it sinks to the interface, but then immediately reacts with water, gets some hydrogen bubbles on it, immediately begins to float to the surface. And it kind of does that back and forth. And so when I said that this is obviously a safer demonstration of sodium, I think in many ways it's also a more effective demonstration of sodium. In my mind, that makes it a winner, because you can see the reaction in slow motion. If I had added that same size piece of sodium metal to water, it would have fizzed, hissed, given probably some smoke, obviously the gas bubbles, maybe a little spark or two or a little bit of ignition, and it would have been over. And what do your students always say? Show it again, show it again. I didn't see it. What happened? What happened? Students don't always see what they're looking at. And in this case, it continues to react. Now it's coated with the hydrogen bubbles. You can see that the size of the piece has really gotten quite a bit smaller, but it goes back up with the bubbles. It adhere to the metal, cause it to float and rise to the top, but then the bubbles come off and the piece sinks back down to its natural level, if you will, which is based on its density, the interface between the mineral oil and the water. Now, a lot of different things you can do as this continues, okay? When we looked at the metal originally, it has a little bit of a shiny surface, and certainly when we had a fresh cut piece, and I don't know if we can focus on the face of that metal where we cut it originally. Let's see if I can pick that up. But right there, you see it does have a shiny face, okay? And that's the metal surface itself. So it is like a metal. It is a metal, obviously, so it's shiny. But once it starts reacting, and if you can see up close on that, it really gets coated with white and looks kind of a little, almost even a little crumbly on the surface, because you do start getting some sodium oxide or sodium hydroxide that are produced. And that, of course, dissolves then as well. But notice that our water layer now has turned pink. And now it's completely pink, and we know that phenolphthalein is an acid-base indicator. It's colorless in acid or neutral solution, and it turns pink or red-violet as the pH goes between 8 and 10. And above pH 10, it's pink. So we know that the pH of that aqueous solution down on the bottom is already 10. So we've clearly produced a base. We think it's sodium hydroxide based on the fact that we had sodium metal and water. We clearly are producing a gas and continue to do so. That's hydrogen gas. And you can see the bubbles at the surface. And that will continue for quite a long time. So this is a great way to almost do the demonstration in slow motion, that repetitive action and so on. You can add more pieces to it. Eventually, I say that the sodium metal sort of seems to get a little tired. It's all right, like I've been swimming here for all day. You know, so you might have to, at the very end, remove the piece and destroy it by reaction with water. There's just a tiny bit left usually. You can add another piece. The first time you do this, you can set this up for your students in your first class of the day. Obviously now the color has already turned to red, violet there, or pink. On the bottom. So for the subsequent ones, they would just know that it has turned, turned basic, if you don't want to set it up again for each and every classroom during the day. But that piece of sodium metal will continue that diving, rising, give it a shot, 1, 2, 3, and we'll then sink again. We call this demonstration safe swimming with sodium because it appears that the sodium metal is actually swimming there. The reaction is, of course, sodium metal with water to give sodium hydroxide and hydrogen gas. And all of the observations are clearly visible for an extended period of time. So a nice way to demonstrate the properties of sodium.